chemical kinetics, we study the speeds or rates at which chemical reactions take place. And most of the times we associate the word kinetic with movement or change. So in chemical kinetics, we are talking of the change, which is the rate of a reaction, which is the change in the concentration of a reaction or a product with time. So you could see that in the chemical industry, the profitability of chemical processes are very, 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 very important. Very, very, very important. Like if you can check industrial chemists and chemical engineers, they often place more emphasis on speeding up the rate of reaction than in maximizing the yield. They want to try and increase the rate of reaction of products. So these chemical engineers and industrial chemists, they have to understand that there are factors affecting the rate of reaction, and they use them to make more products in a shorter time. So that's basically how they use this idea of chemical reaction. So you have to know the meaning of bond energy before we go deeper into this topic. And bond energy is the amount of energy required to break a particular bond in a molecule. So that's what we call bond energy. And this reaction, there are certain reactions that we call exothermic reactions and certain reactions that we call endothermic reactions. So the exothermic reactions is a reaction in which energy is released to the environment in the form of heat and light, and then the temperature of the reaction mixture increases, and then the difference between exothermic reaction and endothermic reaction is that in endothermic, the reaction to which energy must be added continually in order for the reaction to occur. So we are saying in endothermic, the energy should be added continually for the reaction to actually occur. So the temperature of the reaction mixture, it decreases. So that's the difference between endothermic and exothermic reactions. And then there is also the minimum energy, or the minimum amount of energy needed for a reaction to actually begin. We call this one the activation energy. Smallest amount of energy that we need for a reaction to happen. Call it what? Activation. This is basically the revision of grade 11. So when we are doing these chemical changes, we are supposed to know these terms. And then there is the heat of reaction, or we call it the enthalpy change, right? Represented by triangle H. And usually this one is a negative for an exothermic reaction, and it's positive for the endothermic. So you have to know that the heat of reaction is negative for the exothermic and is positive for the what? For the endothermic reactions. So what we are saying is the rates at which chemical reactions are converted into products, they vary widely. You can see, like in cars, the combustion of petrol in a car engine is explodingly faster, but the rusting, of iron is slow. So you can see, like when the motor engine is running, the combustion of petrol is too fast, right? But then if you can check the way a metal rusts, it takes time, it rusts slowly, right? So we are saying certain reactions, right? Virtually all the reactions are what? Are converted to products, right? Whenever there is a reaction, there is an end result. That is what you call what? Product, right? And then we are saying in other reactions, the product, it can break up again to form original chemicals. So products, they can break up and then they can also be reversed. So when we are studying chemical kinetics and equilibrium, we can learn how to manipulate these reactions to suit our needs, because these reactions, they can be reversed, right? They can form more products, and then those products can also be what? Be reversed. So you have to know proton transfers in acid-base reactions and examine electronic transfers, especially in those redox reactions. And it is hard to imagine like a day without electricity. So you have to know that one source of electricity is a battery. So you have to know that the redox reactions, they take place because of electrons that are transferred inside the what? Inside the battery. So these electrons can be harnessed to do work. For example, to light a torch bulb. So that is one of the uses of what? Of a battery. So it means we are transferring this what? These electrons. So some chemical reactions are spontaneous and they provide energy, while others are non-spontaneous, right, reactions, and they need energy to make them happen. So that's also the difference between different chemical reactions, right? Some, they to provide what? Energy. They are spontaneous, but some, they are non-spontaneous. In fact, they need energy to make them what? Happen. So these are some of the things that you also have to know in kinetics, and also when we are doing equilibrium, right? So, but then you have to know that both these processes have important practical applications in our everyday lives, right? So when we are discussing the rate of reaction, it's all about the reaction time, right? Or the speed of reaction for a reactant or a product in a particular reaction, right? So it's basically how fast or slow the concentration of that reactant or product changes. That is, I think, the simple definition of the rate of reaction. It's basically the reaction time, right? Or the speed of reaction for a reactant or a product. Both there is a reactant and there is also what? A product, right? So we are saying how fast or slow the concentration of that reactant or product changes. So, but then this definition is only valid for a single reaction in a closed economy or constant volume. For example, we can say we can boil salt water in an open pot. You would see that the concentration of the solution increases as water evaporates. Like if we are boiling water in a pot, as the water is evaporating, the concentration of the salt is what? Is increasing. That is why you see when all the water is evaporated, maybe the pot will be white, right? But then there is no reaction that is taking place there. It's only the water that is evaporating. So we can say a reaction can be represented as reactants to products, right? So that's other thing that you're also supposed to know. And there are factors that affect the rate of reaction. For example, the nature of the reactants, right? The surface area of the solid reactant is another factor that affects the rate of reaction. And then the concentration of a liquid or gaseous reactant. And the pressure of the gaseous reactant, again, is another factor that affects the rate of reaction. And the temperature at which the reaction is carried out. And the use of a catalyst, again, it affects rate of reactions. So these are some of the things that you have to bear in mind, that rates are always, chemicals are always changing, but then there are certain rates that are faster and there are certain rates that are not what? Faster. Right. And then again, you have to know that all these things, even like we mentioned the issue of a catalyst. A catalyst is a substance that just increase the rate of chemical reactions. And remember, we've got what we call homogeneous catalyst and heterogeneous catalyst. So a homogeneous catalyst is that catalyst or reactant that are in the same phase, right? In the acidification process, like for example of an alcohol with a you can say alcohol with a carboxylic acid, sulfuric acid as a catalyst. You see, the reactants and the catalyst are all in the what? In the liquid phase. So we are saying a homogeneous, we are saying they are in the same phase. But then if it is a heterogeneous catalyst, right, we are saying the catalyst and the reactants, they are different. They are in different phases. Maybe the other one is, we can say, for example, in a Haber process, right? We are saying gaseous reactants, they absorb into what? Solid surface of a finally ionic catalyst. So we are saying without a catalyst, activation energy needed to break is very strong, right? So we need some triple bond which are extremely higher. So there are also other important industrial catalysts like vanadium, and some of them we use in the conduct process. Sulfuric acid, when we use vanadium to produce sulfuric acid, and nickel in the in the hydrogenation of vegetable oils to make what? Margarine. I'm sure we can use that nickel in the hydrogenation vegetable oil to make what? Margarine. So you see that it needs we call them heterogeneous catalyst. So these are some of the things that you are supposed to bear in mind. What is happening, and then from there you can see what are the factors which are really causing these rate of changes. So these things are very, very important. And again, things like activation energy, like the energy that is actually needed to what? To make these reactions fast. So we are saying all chemical reactions that happen in a closed economy are reversible to some extent, right? So we are saying at the start of the reaction, only a forward reaction takes place. So as the product starts to form, the reverse reaction also takes place to a greater or less extent. And some of the products form reactants again. So we are saying we can reverse these chemical reactions. For example, when we fill water in an open beaker with water and we leave it immediately for a period of time, right? You will see that when the water molecules, they will start to evaporate slowly, moving into the space, especially when there is higher temperatures, right? So we are saying the water levels, it decreases until eventually all the water evaporates, especially when temperatures are high. You will see that the water will continue evaporating and evaporating until there is nothing left, right? So that thing is an example of an open system, right? So in an open system, we are saying matter and energy, they can either enter, right, and leave an open system. So you can see that the water is leaving the what? The system. But then we can use that experiment again when we cover a lid of a beaker. You understand? We can cover the lid of a beaker. So when we cover the lid of the water molecules cannot leave. So that's why you see buckets that are closed, the same way they are, right? They are what? No molecule of water will move. So when we close, that is an example of what? Of a closed system. So in a closed system, we are saying matter and energy cannot leave the system in a closed system, right? So we are saying what happens to the water molecules in a closed system. So we are saying initially the rate of evaporation when it was open, it was high, right? But as the space above the liquid becomes saturated with water vapor, more and more water vapor molecules condense back into the what? Into the liquid form. So it's closed. So we are saying even if you can check, like, water will come back, so it's those molecules that they wanted to go, they are now condensing back into the what? Into liquid form. Of course, we cannot actually see the rate but then we are saying the rate of evaporation, it decreases, right, as the rate of condensation increases. That is what happens in a closed. The rate of evaporation, right, it decreases as the rate of condensation increases. So if we leave it undisturbed, right, the system, it will reach a state of equilibrium where the equal number of molecules that evaporate and condense, right, are equal. We're saying it will reach an equilibrium where the molecules that are contained, that are evaporating, they're equal to the molecules that are what? That are condensing, right? Although it's difficult for us to notice that, but that is what will be happening, right? We cannot observe these things, right? But then on the molecular level, the molecules, right, continues to evaporate and condense. This phase of change is reversible and forms a dynamic equilibrium.